Welcome everyone to my channel.
Question number 76. In the displacement method of structural analysis, the basic unknowns are. We know there are two methods of structural analysis for analyzing the indeterminate structure. One is force method and another one is displacement method. In force method, the basic unknowns are force or moments, and in displacement method the basic unknowns are displacements, that means translation and rotations.
Option A is right answer, displacements.
Question number 77. The fixed support in a real beam becomes in the conjugate beam a free end. Option D is right answer. In structural analysis, conjugate beam is an imaginary beam of same length as the real beam, and this method is used for determining the slope and deflection of the original beam. Shear force at any point of a conjugate beam represents the slope at that point of the original beam, and bending moment at any point of a conjugate beam represents the deflection at that point of a real beam or original beam. Question number 78. The width of analogous column in the method of column analogy is. Column analogy method is used for analyzing the indeterminate structures such as beams, frames, etc. And by this method we can find out the fixed end moments, deflection, slopes in these structures. And a column analogy method, the entire beam is converted to a analogous column. The length of the column or section is L, and width of the column section will be 1 by EI.
And EI is the flexural rigidity of the concerned beam.
Option B is right answer. Question number 79. A simply supported beam deflects by 5 mm when it is subjected to a concentrated load of 10 kN at its center. Then what will be the deflection in a 1 by 10 model of the beam if the model is subjected to a 1 kN load at its center? So as per the question, this is the prototype simply supported beam. When at the center 10 kN load is applied, the central deflection is 5 mm, that is prototype structure. And when at the model of the beam the central load of 1 kN is applied, the central deflection is required to be found out for this question. So let's assume the deflection at the center for this model is x mm. So by Maxwell's reciprocal theorem we can write this load, this central load multiplied by this deflection in prototype simply supported beam is equal to the this central load 1 kN multiplied by the central deflection x mm in model of the beam. So if we calculate further, x will be equal to 50 mm, but this 50 is when we don't consider the scale, because the model and prototype structure are differentiated by a scale of 1:10. Okay, so we got the value x equal to center deflection at this beam equal to 50 mm, but deflection at the model will be 50 divided by 10 equal to 5 mm, as the scale is 1:10.
Option A is right answer.
Question number 80. The deformation of a spring produced by a unit load is called flexibility. Option B is right answer. We know for a spring the load equal to K into delta. K is the stiffness of the spring and delta is the deflection for the spring. And from this relation K will be equal to unit load divided by deflection. Okay, and flexibility is inverse of stiffness. So flexibility will be equal to the deformation per unit load. Question number 81. A force P is applied at the support B of the model of scale 1 by 10 of a two-hinged arch as shown in the figure 12.20. This force causes B to move through 100 mm and raises the crown C of the arch by 50 mm. In the prototype structure, if a load of 10 kN is applied at the crown, the horizontal thrust produced will be. So as per the question, this is the model of the two hinge arch ABC. When A horizontal force P is applied at support B. This force causes to move the hinge through 100 mm from B to B dash and raises the crown from C to C dash by 50 mm or 5 centimeter. Now the question is asked here, if at the crown of the two hinge arch in the prototype structure, not at this model, in the prototype structure, if 10 kN load is applied at the crown, then what will be the horizontal thrust produced at the prototype hinge structure? So load at the prototype structure at the crown is 10 kN. So as the scale between prototype structure and the model is 1:10, so the load at the model will be 1 kN, and by Maxwell's theorem we have the load, this load into this distance 10 centimeter is equal to the load at the crown into this vertical distance 5 centimeter. So P will be equal to at the model half kilonewton, but in prototype structure the load will be 10 times more, so half into 10, so 5 kilonewton, as the scale between prototype structure and the model of the hinge is 1:10. Option C is right answer. Question number 82. A fixed beam of span L is carrying a point load P at its midspan. If the moment of inertia of the middle half length is 2 times that of the remaining length, then the fixed end moments will be. Question number 82. A fixed beam, suppose say AB, subjected to a central point load P, and the moment of inertia of the middle half length is 2 times the remaining length of the beam. So half of this length at the middle portion L by 2 has the moment of inertia 2 times, so 2I, and the remaining two portion, this portion and this portion, has the same moment of inertia. Okay, that is I. This part length is L by 4 and this part length is L by 2 and this part length is L by 4.
So we will solve this problem through column analogy method.
If we see this beam as a simply supported beam subject to a central point load, the bending moment diagram of the beam will be like this, triangular in shape, maximum at the center, and the value will be at the middle.
PL by 4.
L is the length of the beam and P is the load, and this diagram is called MS diagram. We know this part has defined moment of inertia and this part has defined moment of inertia. As we'll solve this question by column analogy method, so the next step will be the calculation of load for due to this bending moment. Okay, the load will be on the analogous column due to this bending moment, and the load will be the area of this bending moment diagram into 1 by flexural rigidity EI. So in the next step we can see this is the side view of the analogous column analogy. Then the side view will be like this, length of the beam will be same L and the width will be unity because width is not fixed here. So this is the pressure diagram from the analogous column when subjected to a load. The load will be upwards because under this load, this bending moment diagram, the load is downward. So to counteract this, the upward load will be generated from this analogous column to balance the downward load. That's why the beam is in equilibrium. And if we see the cross section or analogous column section for this beam, the analogous column section will be like this. Okay, the central part L by 2, this zone has moment of inertia 2 times than the remaining two part. So this part and this part has moment of inertia I, and this part has moment of inertia 2I. So cross sectional width will be for this part and for this part 1 by ei, and for this part the cross sectional width will be 1 by 2 ei. As we discussed earlier, this diagram we are watching from the side view, this analogous column giving the upward reaction. Okay, and this diagram is called upward pressure diagram, mi diagram. At this end the pressure is mia, at this end the pressure is mib, because this is the beam of ab as we considered. So to calculate the end pressure a and b, mia mib, the formula will be load by area. So load on the analogous column will be area of the bending moment diagram, that is ms diagram, into 1 by flexural rigidity. So flexural rigidity is not same throughout the beam. Middle part, because middle part has different moment of inertia and the remaining part has different moment of inertia. So load on the analogous column will be for these two part, so 2 into area of this bending moment diagram, half into base length is l by 4 into height will be pl by 8 into 1 by ei. Okay, and the central part l by 2 part has two trapezium, this is one trapezium and this is another trapezium. So for this two part the area of the bending moment diagram will be 2 into half into these two part into this length into the flexural rigidity 1 by flexural rigidity 1 by 2 ei. Okay, so if we calculate, the load will be p equal to 5p l square by 64 ei, and area of the analogous column section will be for this part and this part 2 into l by 4 rectangular area l by 4 into 1 by ei, and for this part the area of the column section will be l by 2 into 1 by 2 ei. So area will be 3 by 4 into l by ei. Okay, now we can easily calculate mia or mib. So mia mib load by area, so if we do, it will be equal to 5 pl by 48. So fixed end moment will be at the end a msa minus mia. So msa means bending moment at the end a when it is considered as a simply supported beam, so that is 0, msa equal to 0 or msb equal to 0. Say fixed end moment at the end equal to minus 5 pl by 48, and fixed end moment at the end b will be same, that will be equal to minus 5 p l by 48. Option B is right answer. Question number 83. A fixed beam AB of span L is subjected to a clockwise moment M at a distance A from the end capital A. Fixed end moment at end capital A will be. A fixed beam subjected to a clockwise moment M at a distance A from the support A and at a distance B from the support B, and the total length of the beam is L. So A plus B equal to L. Now if this is the case, the fixed end moment at A MA will be equal to MB 2A minus B divided by L square, and fixed end moment at B equal to MA 2B minus A divided by L square. So we need fixed end moment at A. So MA equal to MB into 2A minus B by L square. So from the option we have to take only two constant L and A. So by putting B equal to L minus A in this equation, we will get MA equal to minus M by L square L minus A into L minus 3A. Option A is right answer. Question number 84. Consider the following statements. Statement 1. Conjugate beam can be used to determine the slope and deflection in a non-piezometric beam. Yes, conjugate beam can be used to determine slope and deflection in a non-piezometric beam. A non-piezometric beam is the beam where the flexural rigidity EI is not constant.
Statement 2, conjugate beam may be statically indeterminate. No, conjugate beam is statically determinate.
So this statement is wrong. Statement 3, the conjugate beam method gives absolute slope and deflection. This one is correct. So option A is right answer. Question number 85, in a 3-hinge arch. So let's see the difference between 2-hinge arch and 3-hinge arch. For 2-hinge arch AB, length of the arch is L and height of the arch is small h. So degree of static indeterminacy for this hinge arch, for this 2-hinge arch will be r minus 3. R is the number of reaction components. So two number of reaction components will be from this support and two number of reaction components from this support. 2 means one vertical reaction and one horizontal reaction. No moment will be there for hinge connection. So 2 plus 2 minus 3 equal to 1. So degree of static indeterminacy of this 2 hinge arch is 1. So this is a statically indeterminate structure by 1 degree. Now for 3 hinge arch, A, B and C, this is the hinge at the crown, and for this internal hinge at the crown, the value of r dash or the additional equation required due to hybrid joints will be n minus 1. N is the number of member connected from this hinge. So 1 2, these two member are connected at this hinge. So 2 minus 1 equal to r dash equal to 1. So degree of static indeterminacy for this hinge will be ds equal to r minus 3 minus r dash. So 2 plus 2 minus 3 minus 1 for the internal hinge. So ds will be equal to 0. So 3 hinge arch is a statically determinate structure. Now for 2 hinge arch, the maximum value of horizontal thrust will be 25 L by 128 into h, and maximum value of horizontal thrust will be at the center,
When unit load will be at the crown of the hinge.
and ILD for horizontal thrust for 2 hinge arch is parabolic. Next,
For 3 hinge arch,
the ILD for horizontal thrust is linear. The diagram is triangular in shape. Okay, and maximum value is L by 4h. H is the height of the arch and L is the length of the arch, and maximum horizontal thrust will be available when the unit load will be at the crown of the 3 hinge arch. Suppose for this 3 hinge arch ABC, we are taking a section XY at a distance small x from the support A. So when unit load is placed at this section XY, the sagging bending moment will occur when the unit load will be at this section itself. But when the unit load will be at the crown of this 3 hinge arch, the maximum hogging bending moment will occur. So option C is right answer. Statement 2 and 3 are correct. Number 86, the influence line for horizontal thrust in a 2 hinge parabolic arch is parabolic. Option A is right answer. Question number 87, for a single point load W moving on a symmetrical 3 hinge parabolic arch of span L, the maximum sagging moment occurs at a distance x from the ends. The value of x is, suppose this is the symmetrical 3 hinge arch as of like question number 87. Okay, so maximum sagging moment will occur at a distance x from the supports A, we know, and the question is asked here, what is the value of this x, and the load W, moving load W is acting at this section x. Okay, so the value of x from the support A will be 0.211 L for this maximum sagging moment. 0.211 L. Option A is right answer. Question number 88. Muller-Breslau's principle for obtaining influence lines is applicable to Muller-Breslau principle can be applicable to trusses, beam frames for determinate as well as indeterminate structures, but
under the linear elastic behavior of the material and where the material obeys the Hooke's law. So option A is right answer.
question number 89. Consider the following statements in regard to finding stresses in the truss member due to moving loads. Statement 1. The stress in a wave member is given by the influence line of shear force for the panel containing the member. Statement 2. The stress in a wave member is given by the influence line of bending moments for the node point opposite to the member. Statement 3. The stress in a chord member is given by the influence line of shear force for the panel containing the member. And statement 4. The stress in a chord member is given by the influence line of bending moment for the node point opposite to the member. Statement 1 and 4. Option B is right answer.
Not going deep into the analysis, and just to give you an idea of this question.
This is a Pratt truss consists of 1, 2, 3, 4, 4 panels of equal length. Total length of the truss is L, and up to this point U4, U1 to U4 the length is A, and U4 to U5 length is B, and height of the truss is H, and the truss is supported hinged at end A and roller supported at the end B. So to draw the influence line for a specific member, we find the axial force in that specific member every time the unit or moving load visits a joint. Suppose we are determining the axial force or stress in the member, in the OM member L2 U4. OM member means vertical and diagonals member of the truss. So suppose we are determining the stress or force, axial force in the member L2 U4 of the truss. So we know when unit load is at A and B, all the member forces are 0. So our graph of influence line starts at 0 and ends at 0. Okay, now we will plot this graph. When if we want to find this ordinate at L1, the height of the graph, then we need to place the unit load at L1 and calculate the force at L2 U4. Okay, then we will get this height and we will get the member force at L2 U4. At this point, when we want to calculate the height of the ordinate of influence line, then we will place the unit load at here, and we will and calculate the axial force in the member L2 U4. So we will get this height. When the unit load will be at here, we will calculate the value of member force L2 U4. So this value will be the height of this graph. So this is the baseline. So above this baseline, the graph is positive, that means the member is in tension, and below this line the member is in compression.
So at this panel containing the member L2U4, shear force influence line diagram is drawn to get the stress in the wave member L2U4. So statement 1 is correct.
Now if we want to determine the member forces or stress in the bottom chord L2 L3, and that will be determined by the influence line of bending moment for the node opposite to the members. That means suppose we want to determine the member forces in the stress in member L2 L3. Okay, so of this panel, this is the alternate. U4 is the opposite node. So for this node we will draw the bending moment influence line to get the stress in the chord member L2 L3.
So in question statement 4 is also correct.
Question number 90. In which of the following truss members the stress depends upon whether the load is moving on top chord or bottom chord? This is the simple cross section of a truss. This is top chord and this one is also top chord. This is bottom chord of the truss, and 1 2 3 these vertical members are verticals of the truss or wave member of the truss, and this inclined members 2 is the diagonals of the truss, diagonal member of the truss.
The stress in vertical members and diagonals of the truss is significantly affected by the load's position, and when the load is directly over the vertical member of the truss, it induces direct forces. And when this load is over the diagonals of the truss, then the forces in the member will be either compression or tension. So in my opinions, wave member of the truss or verticals and diagonals are the members on which the stress depends upon whether the load is moving on top chord or bottom chord. So option D is right answer.
Question number 91. For approximate analysis of building frames under vertical loads, the point of inflection is assumed at 1/10 of the span length from the each end of the beam. Option C is right answer. So there are mainly three methods for the analysis of lateral loads in portal frames or multi-story building. Okay. So the methods are portal method, cantilever method and factor method. So method 1, portal method. The assumptions are for this method: the shear force in the interior column is twice the shear force of an exterior column, and there is a point of inflection at the center of each column and each beam of the portal frame. Point of inflection means the point where bending moment is zero.
And where curvature of the bending moment changes.
Next, cantilever method. The assumptions are the axial force in each column of a story is proportional to its horizontal distance from the centroidal axis of all the column of the story, and there is a inflection point at the center of each column and beam. Next, factor method. This method is more accurate than either portal method or cantilever method, and this method is based on the elastic action of the structure. This portal method and cantilever method will yield good results when the height of the building is approximately more than 5 times its least lateral dimension. Question number 92. In a cantilever method of lateral load analysis, which one of the following assumptions are made? So option C is right answer. Only statement 2 is correct. Question number 93. The factor method of analysis building frame is more accurate than either portal or cantilever method, and based upon the slope deflection method of analysis. Both statements 1 and 2 are correct. So option B is right answer. Question number 94. A rigid cantilever frame ABC is fixed at end C. As shown in the figure 12.21, it carries a point load P at A. Neglecting the axial deformation, the horizontal deflection del HA of the point A will be. So as per the question, a rigid cantilever frame ABC consists of two members AB and BC. AB has a length of L and BC member has a length of H, subjected to a vertical point load P at the end A, and the flexural rigidity of the frame EI is constant throughout the frame. Now we have to determine the horizontal deflection at the point A.
Now we will use Castigliano's second theorem to find the deflection at point A.
Castigliano's second theorem states that the partial derivative of the strain energy of the structure with respect to the applied force is equal to the deflection of the structure at the same point along the line of action of the applied force. So, by the Castigliano's second theorem, we can determine the line of action of the constant deflection
By the applied force,
and that will be in the same line of action as the applied force, and it will be at the same point where the force will be applied. At point A there is no horizontal load, so first we have to consider a horizontal load, that is fictitious load, whose value is equal to 0. That is an imaginary load. So the fictitious load capital F is equal to 0.
we have to consider this horizontal load at A because we also need to find out the deflection at the point A.
We also know that the formula for strain energy of a structure is equal to Wi equal to integration m square ds by 2 ei. M is the bending moment and d is the direction and ei is the flexural rigidity of the structure. So total strain energy of the structure will be, the structure consists of two member AB and BC. For member AB, let's take a section x dash at a distance x from the point A. So At this point, at this section xx, the moment will be p into x square, because m square, and the direction will be dx, x direction, divided by 2ei, but the total length of the member AB L, so limit 0 to L plus, for this member BC, the strain energy will be, suppose this vertical, for this vertical member we are taking a section y dash at a distance y from the point B to this section. So now for this member, the strain energy will be m square into ds divided by 2ei. So m, the bending moment at this section, will be, for this load, p into l plus, for this horizontal load, f into this downward vertical direction y, so fy whole square into the direction will be vertical dy divided by 2ei. Now, by the Castigliano's second theorem, we know if we make the derivative of the strain energy of a structure with respect to the
concerned force at the point, then we will get the deflection
at the respective point, and that is A.
and the direction of the force and the deflection will be same.
So, as we considered the horizontal fictitious load F at the point A of the structure, then we will get the horizontal deflection at the point A. So,
by the
we got the
Castigliano's
strain energy
second
of the
theorem.
structure. Now, if we make the derivative of the strain energy acting at the point
with
A,
respect to horizontal
then
force
the
F,
value will be 0 for this term, because there is no fictitious load F at this value, so this term is 0. Next, for this term, the integration value will be first 2 into PL plus Fy into y dy by 2ei minus 1 by 2ei integration 0 to h ply plus Fy square into dy. Now if we calculate, we will get del HA equal to 1 by ei into ply square by 2 plus Fy cube by 3, and the limit will be 0 to h. Now if we put the fictitious load F equal to 0 in this term, so we will get the last value where y will be equal to h. This is the maximum value, so the final deflection value will be PLH square by 2ei. Option A is right answer. Question number 95. Consider the following assumptions in the analysis of a plane truss. Assumption 1. The individual members are straight.
correct, the individual members of the perfect frame, that is plane truss, are straight.
Assumption 2. The individual members are connected by frictionless hinges.
This one is also correct.
Statement 3. The loads and reaction act only at the joints.
Correct statement.
Option D is right answer. Question number 96. Two bars AO and BO are of uniform area A each and are hinged at O as shown in figure 12.22. A load W is applied at O, so the vertical deflection at the point O will be.
Again we will solve this through Castigliano's second theorem.
Castigliano's second theorem states that the partial derivative of the strain energy of the structure with respect to the applied force is equal to the deflection of the structure at the same point along the line of action of the applied force. So, by the Castigliano's second theorem, we can determine the line of action of the concerned deflection, and that will be in the same line of action as the applied force, and it will be at the same point where the force will be applied.
So in this question, a vertical load W is acting downwards at the point O, and also the vertical deflection at point O is required to be found out. So Castigliano's second theorem is applicable to this system.
So as per question, two bar AO and BO are hinged at O, and from this point O a downward load W is applied, and suppose assume the two bars AO and BO of uniform area is attached to a ceiling, that is AB. Okay, let's assume now force in the bar AO, let's assume is FAO, and force in bar BO is FBO. So the vertical component of the force in bar AO will be FAO sine 45 degree, and the vertical component of force in bar BO will be equal to FBO sine 45 degree, and horizontal component of force in bar AO will be equal to FAO cos 45 degree, and horizontal component of force in the bar BO will be equal to FBO cos 45 degree. Now, for the sake of equilibrium, we know that summation of all the forces in vertical direction is equal to 0. So, as this load is downward, the forces in the both the bar AO and BO will be upward, and that's why the system is in equilibrium.
So from equilibrium in this plane, the summation of all the vertical forces is equal to 0.
If we do that, the vertical component of forces will be FAO sine 45 degree plus FBO sine 45 degree equal to the opposite directional load, that is W. So equal to W. Now if we solve, FAO plus FBO will be equal to root 2 into W. Again we also know that from equilibrium summation of all the forces in horizontal direction is equal to 0. So the horizontal component of force in bar AO will be equal to horizontal component of force in bar BO.
And their direction will be opposite to each other.
So FAO cos 45 degree is equal to FBO cos 45 degree. So from this we can say FAO equal to FBO. Now this is equation number 1. So FAO equal to FBO we got. So in this equation if we put FAO equal to FBO, so we will get FBO equal to W by root 2 and FAO equal to W by root 2, because both are same. Now U is the total strain energy stored by the two bar AO and BO of uniform area. So the total strain energy stored by the two bar will be UAO plus UBO at the point O, and the formula for strain energy is W square L by 2 AE. So for bar AO the strain energy will be W1 square L by 2 AE, and for bar BO the strain energy will be W2 square L by 2 AE. A is the area of the bar and E is the modulus of elasticity of the two bars. So W1 is the force in the bar AO and W2 is the force in the bar BO. So W1 will be equal to W2 because we got W by root 2 is the value. So by putting this value into this equation, the total strain energy value will be W square L by 2 AE. This is the total strain energy by these two bar. Now if we differentiate this strain energy with respect to load, with respect to downward load W, then we will get the vertical deflection at point O, because the strain energy stored at the point O by the two bar.
And this is the Castigliano's second theorem.
Now if we differentiate the strain energy with respect to W, then we will get vertical deflection at point O, and if we do that we will get the vertical deflection value at O is equal to WL by AE. Option A is right answer. Question number 97. The influence line for bending moment at section X MX at a distance 4 meter from the left support of a simply supported girder is shown in the figure 12.23. A uniformly distributed load of intensity 2 ton per meter longer than the span crosses the girder from left to right. So the maximum bending moment at section X is equal to, so this is the simply supported girder AB, and the uniformly distributed load moving from left to right, and the load is longer than the span of this girder AB. Okay, so the maximum moment will occur for this beam. So at this section XX taken on the simply supported girder AB, that is at a distance 4 meter from the end A, and this is the ILD diagram for maximum bending moment at section X. The ordinate of the influence line diagram is 3 and this base length is 16 meter. So maximum bending moment at section X will be intensity of loading into area of this ILD diagram for the moment at X. So intensity of loading is 2 ton per meter into the area of this ILD diagram will be half into base length is 16 meter and the height, that is the ordinate of the ILD diagram, that is 3. So 48 ton meter. Maximum bending moment at X section will be 48 ton meter. Option C is right answer. Question number 98. A one-storied rigid portal frame ABCD carries load P and Q as shown in the figure 12.24. It is hinged at the two supports A and D. The structure is statically. So this is the rigid jointed portal frame ABCD subjected to vertical loading P at this point and Q at this point, and EI is the flexural rigidity of the frame, that is constant throughout the frame. Now the degree of static indeterminacy of this frame will be 3m plus r minus 3j. M is the number of members of the frame, R is the number of reaction components from the support of the frame, and J is the number of joints. So number of member will be 1, 2, 3, and number of reaction components from these two support end A and D will be 2 from this end and 2 from this end. So 4, because from hinge support we know two reaction we will get, that one is horizontal and another is vertical. So 2 from this support and 2 from this support, so total R will be equal to 4, and number of joints will be 1, 2, 3 and 4. So by putting all the value in this equation, degree of static indeterminacy, we will get the value ds is equal to 1. That means the structure is indeterminate to first degree. Option B is right answer. Question number 99. The influence line for shear at section X Fx at a distance of 4 meter from the left support of a simply supported girder AV is shown in the figure 12.25. The shear force at a section X due to a uniformly distributed dead load of intensity 2 ton per meter covering the entire span will be. So this is the simply supported girder AB subjected to a uniformly distributed load 2 ton per meter, and this is the section X dash, and at this section X dash the influence line diagram for the shear force at X section is given. This is the influence line diagram for maximum shear force at section X. So maximum shear force at section XX will be the loading intensity on the girder into area of positive influence line diagram minus area of negative influence line diagram for the section. So loading intensity is 2 ton per meter into the area of the positive triangle will be half into this base length is 12 meter into this ordinate 3/4 minus this triangle area, that is half into this base length 4 meter into ordinate of this negative triangle is 1/4. Now if we calculate, we will get maximum shear force at this section X dash will be 8 ton. Option A is right answer. Question number 100. Consider the propped cantilever shown in the figure 12.26 and the fixed beam shown in the figure 12.27. So figure 12.27, the beam is subjected to a uniformly distributed load of intensity 2 ton per meter, and in figure 12.27 the fixed beam subjected to a same intensity of loading 2 ton per meter. Length of the both beam is 6 meter. Now consider the following statements regarding the two figures. Statement 1, the fixed end moment of A of the propped cantilever is 12 ton meter, and statement 2, the fixed end moment at A of the fixed beam is 6 ton meter. So figure 12.126 is a propped cantilever beam. For propped cantilever beam, the bending moment at the end A will be WL square by 8 and at end B is equal to 0, and for maximum positive bending moment will be 9WL square by 1 28, and this length of the positive bending moment is 3L by 4. So fixed end moment at the end A will be WL square by 8. W is 2 ton per meter, L is 6 meter. So by calculating we will get fixed end moment at A is equal to 9 ton meter. But in figure 12.27 the beam is a fixed beam indicated by AB of length 6 meter and same loading intensity 2 ton per meter. The fixed end moment at both end A and B is same, and that will be equal to WL square by 12, and that is minus. So fixed end moment at A and B will be equal to WL square by 12. So W is equal to 2 ton per meter and L equal to 6 meter. So by calculating we will get fixed end moment at A or B is equal to 6 ton meter. Option D is right answer.